All right. You guys have questions or anything?
Yeah, give me a second. What happened to your face first? Where'd that thing go? Where'd that dead beaver go from your chin?
All right, let's talk about this before I answer your questions. Let's talk about this real quick. This might answer your questions. It says, let theta be an angle in standard position. Let P be in the point x, y be a point on the terminal array of that angle. It says, if R equals the square root of x squared plus y squared is the distance from the origin to the point P, x, y, then these following 6 trig ratios are true. And we call them trig functions in this case. Here's the idea. I'm just trying to lay this out generically for you first, and then we'll go to GeoGebra and show this kind of working in actuality with specific values. So what they're saying here is that you are going to put this thing in the coordinate plane. It says it had to be in standard position. So that means this side here, okay, that is your initial ray. It has to stay there on the positive x-axis. Okay? Your terminating ray is that there. Okay? Your terminating ray stops at a point P, comma, x, comma, y. Or so P being the point x, comma, y. All right? What that does then is if I go from that point and I go straight down to the x-axis, it creates a right triangle right there. Correct? Is this now your opposite side of theta? Is this your adjacent side? Is this your hypotenuse? Okay. Now, we know, based on Pythagoras, that the adjacent side squared plus the opposite side squared should equal the hypotenuse squared, right? Okay. Well, can I rewrite so the adjacent side is the x value of that point, right? Does that make sense? To get to that point, I got to travel over x units and then up y units, right? So the adjacent side is x. The opposite side is y. The hypotenuse, we're redefining it as the letter r. We'll talk about that here in a moment. But then if I want to find that red distance, I'll just take square root. Okay. Oh. Now, this is going to be a distance. This red thing, this red segment is a distance. So it's positive, and this is always going to be a positive number. So R 100% of the time is going to be a positive number. Okay? So that needs to be something that we commit to memory. But now, if that's the case, and I want to find, let's say, the sine of this theta, can't I just look at that y value, whatever it is, because that's the opposite side length, right? And divide it by the hypotenuse, which is the r value. So sine of theta is now defined based off of using the opposite side of the y coordinate and the length of r. Does that make sense? Okay. So let me show you that in GeoGebra real quick. Let's take this triangle, and right now the way I've got this set up, let's get that out of there. I'm looking at right now with that triangle right there with obviously point A prime Okay, so we're looking right there, A prime being 3.66, comma 3.41. That's the ordered pair, okay? If I look over on the left-hand side where I've actually got some calculations going on, right now, that calculation right there is as if you took your calculator and typed in sine of 43 degrees. It's going to spit back this 0.68, okay? What I want you to understand is that when you type that into your calculator has absolutely no idea that you're looking at a triangle that has a side of 3.41, a side of 3.66, and a side of 5. Does that make sense? Okay. But it still gives me 0.68 back regardless. Okay? When I look at my triangle and I actually divide the y value out of that ordered pair by the r value of 5, do I still get the same 0.68? That makes sense? Okay? So what our calculator is doing is that our calculator understands, or our calculator knows, that no matter what these values are, 3.41 or 5, or if they're, in this case, and now I'm looking at this little maroon triangle, if it's 2.32 divided by 3.4, okay, that opposite side divided by that hypotenuse, okay, so this point D here would be the ordered pair. Okay, that point D, let's see if it will show up if I just, I thought if I hovered it would show up on it. Let's put the name and value. So point D now, 2.32 is the y value, 2.32, divided by the r value in this case, which would be that highlighted segment of 3.4. Divide that, does it still give me 0.68? Okay, so as I move that point D around, does the numerator and denominator change in that bottom fraction? Yeah, but does their quotient ever change? No. Okay, and that's because that triangle right there, okay, that maroon triangle, has a right angle and a 43-degree angle, right? So that means this angle here, 47 degrees, has to be the same there as it is there, right? Does that triangle have a 43, a 47, and a 90? Does this one have a 43, a 47, and a 90? That kind of makes sense? So all of these triangles here are similar. And if you remember back to geometry, we talked about it probably on Tuesday of last week, that any two right triangles that are similar by AA, angle, the side lengths are proportional, meaning when I compare the opposite side to the hypotenuse of that triangle, it's the same ratio as the opposite side divided by hypotenuse of any other triangle with the exact same angles. Is that right? So that's why we know our calculator is going to spit back this 0.68, because our calculator is programmed with the understanding, okay, that opposite side divided by hypotenuse is identical to that one. Okay, so it doesn't, the calculator bypasses this. I don't even care what your values are. I know they're going to evaluate the 0.68. Okay, and I'll show you when we get there. It'll be a while, but I'll show you how your calculator is actually generating that 0.68. Okay, so I think we finished Friday, and I asked you what eventually, instead of dividing by 3.26 to get that 6.8 or 0.68, what is a really nice number to divide by? 1. A really nice number to divide by is 1. So let's make this R1. Now, it's going to be hard for me to drag it this way. I can't really, unbelievable. That's rounding error, though. So let me do it this way. Let's change this to 90. And now I can snap that to 1. Okay. Now I'll move back to 43. Yes, please.
So if you don't do like one problem in the assignment, is it all incomplete?
No.
Okay.
All right. So I'm looking at this stuff now. What I've done is I've now taken. So we started that overall triangle, right? This had a radius of 5. I'm now going to look at this. I'm going to zoom in on it, but I'm going to look now at that red triangle. That red triangle, that now has a radius, that little highlighted segment there, that's a radius of 1. Does that make sense?
Yeah.
Okay. This ordered pair is now 0.73, comma 0.68. Does that make sense? Does that hold true to what our sign was as the opposite side divided by the hypotenuse, right? Okay, but when the hypotenuse is 1, don't we see that the sine value is just the same thing as your y value? That make sense, everybody? Okay, so what we like to be able to do, guys, is to kind of demonstrate this real quick for you, is that if we rotate here, okay, and show kind of the infinite number of angles that we could deal with and the infinite number of right triangles that we could deal with, we get those two circles generated. One circle, the outer one, has a radius of 5, and there are an infinite number of circles like it that could have a radius of 5.5, 5.25, 6, 7, whatever, okay? But that one smaller one has a radius of what? 1. Okay? And whenever something has a value of 1 that describes it, is the only thing that, it's the only dimension that dictates the size of the circle is the radius, and it's a 1, we refer to it as a unit. Does that make sense? So we call that a little circle on the inside the unit circle. Okay? And what's going to happen, this is just going to give you an idea of where we're taking this information, is that everything we learn in Chapter 5 is going to be retaught in Chapter 6, but using a different perspective. Right now, it's the perspective of looking at these right triangles. Okay? My hope is, though, you can see that this little right triangle here had a pretty big helping hand in generating this circle, right? So Chapter 6 is going to be using that circle to do all the things that we're doing in Chapter 5. Okay? And it's called the unit circle approach. Called the unit circle because of that value of 1. Does that make sense?
Yeah.
Okay. There are other things that you guys, maybe in physics, you guys talk about unit vectors in physics? Okay, unit vector, maybe I and K and J. Ever hear of those? Okay. All right. Dot product, you guys do dot product, cross product, anything like that in physics? All right. If you're talking about maybe orthogonal, you guys ever talk about orthogonal vectors in physics? Okay.
I'm the only one that answers, and I'm not in physics. I just want you to know.
You're the only one that verbally, you're not the only one, but you're one of the main ones that verbally answers. They all shake their head yes and no. Okay. So there are other things throughout mathematics that carry a quantity of 1, and we call those objects unit whatevers. Okay, a unit vector, unit circle, that type of stuff. All right. So when we get back to this here, okay, the idea is it doesn't really matter how big your circle is or how big that R value is. Okay. Conveniently, we like it to be 1, and that's what Chapter 6 is all about, is when that R value is 1. But it doesn't matter, okay? So what I want you guys to know is that the sine of theta is always, it's opposite over hypotenuse, but when we're in the coordinate plane, the opposite is always going to be your y coordinate, and the hypotenuse is always r, which was the square root of x squared plus y squared, okay? So here's the idea. If I want the sine of any angle, all I need to know is an ordered pair, because that ordered pair, on the terminal side, because that ordered pair generates, obviously, the y value, and it also generates the r value. Does that make sense? Okay. The cosine of theta is the same thing, except for now it's x over r. Okay, it's the adjacent side divided by hypotenuse. Well, the adjacent side is always going to be x. Okay, and r then is still the square root of x squared plus y squared. Okay. Tangent, a little bit different. Tangent doesn't incorporate r, because tangent is opposite over adjacent, right? So if I want to find a tangent of any angle, all I need to know is a point on the terminal ray, and then I divide them, y divided by x, and that gives me the tangent of any angle. And then you see the reciprocals below them, okay? The only thing you have to pay attention to is the reciprocals. Now, these are functions, okay? Basically, the input is going to be your theta, and the output essentially is the y over r stuff, or x over r, whatever. The thing we have to realize that when we do cosecant, secant, or cotangent, okay, and tangent, remember r is always positive. Okay, so r will never be 0. If r was 0, you'd have no triangle, right? Okay, that would be all those points would be condensed on the origin. Cannot divide by 0 in all of those. Okay, so if we were thinking about graphing things, if you've seen sine waves or cosine waves or anything like that, if you've ever graphed the tangent, the cotangent, the secant, or the cotangent, or the cosecant, there are asymptotes because of the division by 0. Okay, so we'll talk about that stuff eventually. One thing that I think is important to talk about here is another way of talking about tangent real quick. We just said tangent of theta is equal to y over x. What was sine? Y over r. What was cosine? X over r. I would. Some of these I'll give you, some formulas I give you, some I don't. Because this is a very common one that you shouldn't have to be given. If I've got y over r And I'm just going to put this division sign here real quick. So I'm going to divide the right-hand side of these two fractions, or these two ratios. Okay? How do I divide a fraction by a fraction? Multiply by reciprocal. So that's going to go to 1 on the bottom, right? Over here, multiply. What happens to the r's? Cancel. And this leaves me y over x, right? Well, that's exactly this y over x right here, isn't it? So when I divided sine by cosine, it gave me y over x, which was the same as that y over x, which must mean that it's the same as that, right? So another way of talking about tangent is to call it sine divided by cosine. That's a fact. It's called an identity, but we'll talk about identities later. But that is a trigonometric fact that we need to commit to memory. Okay? Another way of talking about tangent. So here's the thing. We got 6 trig ratios, right? We got 6 trig ratios. And they always ask us, and we saw a question last week about this, they said, go ahead and when we give you cosine is 3/4, find the other 5. This basically says, we know we can find 3 of them by taking reciprocals of the first 3. So find sine, cosine, tangent. Take the reciprocals, you get secant, cotangent. This is essentially telling us if you find sine and cosine right off the bat, you're done. Because then it's just dividing those two things to find your tangent. And then once you have all 3, then sine, cosine, tangent, you find their reciprocals, and you've got all 6 now. Does that make sense? Okay. So there's little things throughout the year that are going to be like that that we are going to have to work with and deal with. Now, the argument is, do I have to memorize that? No, but yes. Okay, and this is what I mean by that. Will I give that information to you? Probably. Okay, but here's the thing. You're going to use that so much. If you don't inherently learn it within a week or so, then you probably shouldn't be in a college class or a college level class. Okay? This here, I don't want to scare anything. This is a trig cheat sheet. It's a cheat sheet. It does not mean that every trig function or every trig relationship that we talk about throughout this course is on here, but there's a lot on here. Okay? But it's not all of it. I'm just going to scroll through this real quick. We're currently talking about this set right here. Now, this set right here, ultimately, in relationships that we're going to analyze, create everything else I'm going to show you. That's a lot of formulas, right? And more. Okay? A lot of stuff going on there, right? Okay? But they all stem from SOHCAHTOA, which ultimately stems from Pythagorean theorem, stuff like that, right? Does that make sense? So, on this test, obviously when we're on like a unit test or whatever, my concern is that because a lot of these formulas, if we look at this, I'm going to look at these sum formulas down here in a minute. Look at these formulas here. Would you agree that this group of formulas right here are very similar? Okay? Very similar. The things that change are, that top one it's sine alpha, sine beta, bottom one it's cosine alpha, cosine beta. And that's then the plus sign and minus sign in the middle on the right-hand side change. Okay? Those little intricacies I don't want to be the issue for like a bad quiz grade or a bad test grade that you transpose those on accident from memory. Does that make sense? So I will give those to you, okay? Now, are those as hard to remember as sine divided by cosine and sine tangent? Shouldn't be, okay? But you see on this one that does show up as a formula. But we'll use this thing probably, I don't know, upwards of 1,000 times this year. Okay, so it'll be something that you guys just know. When we deal with the trig ratios and these trig functions, sometimes we get positive and negative values back. Okay, take your calculators out real quick. All right, if I'm in, just go to degrees.
And that is, what?
Mode.
Mode. Degrees. Okay.
I don't know what happened to my calculator, but I can't get it to show up in the right spot. All right, well, I can't show you like the zoomed in version. But we're going to just type in like cosine of, go 30 degrees. Cosine 30 degrees. 0.866, right? Okay. Type in cosine of 150. Same number, but negative, right? Okay. So I want to talk a little bit about how we should know that whenever I ask you find cosine of, say, 30 degrees, or cosine of 150, or cosine of 210, or cosine of 330, okay, how we should know that those are always 0.866, but some of them are positive, some of them are negative, okay? And in all these relationships can all be kind of brought back to this chart here, okay? But what I want you guys to understand, you know, when you're in first grade, second grade, you start to learn how to add, right? Add and subtract, right? What was the first thing that you ever did in a math class?
Introduce yourself.
You counted, okay? All right, so I want to know how many marks. So first grade, maybe before that, preschool, okay? You learn how to count, right? So I gave you a bunch of markers, and I asked you to count them. And you tell me how many are here, right? How many? 8, right? Okay, so you just count. 1, 2, 3, 4, 5, 6, 7, 8, right? The next thing you learn, okay, is, okay, Mr. Fay has a group of 2, and he has a group of 6. 2 plus 6 is 8. But why does that happen? Because when I merge those two groups and I go back to pre-K and count, I get 8 in that group, right? Okay. Then the next thing you learn how to do is what? Subtract. So I say, Chuck, here are 8 markers. Chuck, give me 3 of those markers. How many markers does Chuck have left over?
8 minus 3.
Go back to pre-K. 1, 2, 3, 4, 5. You count how many is in that group, right? Okay. So what did we just demonstrate there? Adding, subtracting are quick ways of doing
Math.
counting, right? Adding, subtracting are efficient techniques for counting. Because I just did that. All right, whatever. So the next thing you did is that you took 2, 2, 2, and 2, right?
Yeah.
Okay. So I got 4 groups of 2, and I asked you, how many do I have? You did what with them?
Multiplication.
Multiplied. So you got
8.
But really what happens when I go 4 times 2 is I take those 4 groups of 2 and I cluster them together, and I go back to pre-K and I count how many are in that cluster. How many are in that cluster? 8, right?
8.
So multiplication is a quick way of
Counting.
Good. Okay. So now here's another thing. Let's say I've got,
7.
let me get one more marker here. Okay, I got 9 markers total.
All right.
Okay? And I take 3 away. And then I take 3 more away. And I take 3 more away. So I have no more markers, right? And then I count how many groups of 3 I just made. How many groups of 3 did I make?
3.
3. So I started with 9, grouped them in groups of 3. How many groups did I get? 3. What did I just do there?
Multiply by 1/3.
Division, which is repetitive subtraction, right? Okay? Which subtraction is a quick way of counting. So division, quick way of counting, right?
Yeah.
All right, so here's my argument. Throughout first grade, second grade, third grade, fourth grade, all the way up to whenever you stopped working with your times tables, multiplication tables, division tables, all that kind of garbage, you learn fast techniques for counting. You learn skills so that when I ask you, what is 17 times 34, you don't have to make 17 groups of 34 hash marks and then go count all of those again, right? You just learn those facts. That's kind of what we're doing here. We're learning some fundamental facts that all stem back to SOHCAHTOA, ultimately, and a squared plus b squared equals c squared. That's going to allow us to do some math later on much more efficiently. Does that make sense? Yeah. Okay. So we're kind of building that foundation here. One of the key things for that is knowing the plus and minus aspects of our ratios. All right. We want to know, how do we decide whether our sign, S-I-G-N, should be positive, right? Okay. Sign and sign, S-I-N-E and S-I-G-N are what to one another? Sign and sign. They are called what in English class? Homophones. Okay. So we run into a big issue. Because I want to ask you, what's the sign of this? And you're going to think, well, what is the opposite over hypotenuse? And I'm actually asking, what is the plus or minus aspect of it? Okay. So I will spell it out, S-I-G-N, when I'm talking about the sign, right?
Why did you say sign G?
Yeah.
Big nerd.
Let's talk about this. If everything is based off of an ordered pair, we just talked that sine, cosine, and tangent are based off of using x's and y's, right? And then those generate the r value, right? The radius, okay? That means that any point that is in this quadrant is positive, comma, positive, right? Okay? That means that r there is going to be positive. R over here, we said is going to be positive. R here is going to be positive, and R here is going to be positive. I'm going to write that down. But whenever I take for instance, the sine value in the first quadrant, it's going to be a positive divided by a positive, right? So is the sine, S-I-N-E, going to have a positive S-I-G-N?
Yeah.
Yes. Okay. What about cosine? Is cosine going to have a positive sign? Is cosine x over r? X in the first quadrant is positive. R in the first quadrant is positive. So we got positive divided by positive. Cosine should be positive, right? Does that make sense?
Yeah.
Tangent, we just said, was sine divided by cosine, right? Yeah. Well, you just said sine was positive, cosine was positive. So I divide a positive by a positive, what do I get? Positive. Okay? So the tangent's positive. So if the sine is positive, is its reciprocal positive?
No.
What?
Yes.
What's a reciprocal?
Oh, I was thinking opposite.
Okay, so a reciprocal, we just flip the numerator and denominator, right? So if the sine is positive, cosecant's positive. If cosine is positive, secant's positive, right? If tangent is positive, cotangent's positive. So we have all of our trig ratios. All of our trig ratios are positive when our angle terminates in the first quadrant. Okay, so if you had like a chart that, maybe we generate a calculator that's got sine, cosine, tangent, secant, cotangent, all listed, and then I can change the angle on all of those from 0 to 90. Any one of those numbers, 0 to 90, is going to generate all 6 of those things to be positive values.
Why did it say all?
Because all of them, all 6 trig ratios are positive in the first quadrant.
I'm talking about on the graph.
Right here.
Yeah.
Yeah. All 6 trig ratios are positive in the first quadrant. It'll make maybe more sense when we go to this one. This ordered pair, any ordered pair in the second quadrant, what's the x-coordinate going to be?
Negative.
Negative, and the y-coordinate is?
Positive.
Positive. Okay? So that's x and that's y, right? R, again, is positive, right? So I go sine, it's y over r, so it's positive over positive. What's that result? What's that quotient? Positive over positive is a?
Positive.
Positive. Okay, so sine is positive in the second quadrant, right?
Okay.
Cosine is x over r, right? Negative divided by a positive. What's a negative divided by a positive? Negative. So cosine is negative in the second quadrant. So that's why when I asked you cosine of 150, and it gave you back negative 0.866. Why was it negative? Because 150 terminates in that quadrant, right? Terminates in the second quadrant.
You want us to memorize this?
Yes. Tangent is sine over cosine. You just said sine was positive and cosine was negative, so it's a positive divided by negative. Negative. So tangent is negative. So sine was positive, cosine and tangent were both negative. So cosine's reciprocal secant should be negative, and tangent's reciprocal cotangent should be negative. Sine's reciprocal is positive.
Yeah.
Okay. And we'll talk about this phrase here in a moment. But now I've got negative, comma, negative. Okay. So R again is positive. So then sine is a negative divided by positive, so it's negative. Cosine is a negative divided by positive, so it's negative. So sine and cosine are negative in the third quadrant. Tangent, we said, was sine divided by cosine, right?
Yeah.
Well, sine was negative, cosine was negative. Negative divided by negative is a positive. So that's why it says tangent down there. Tangent is the only one that is positive. And then cosine over here is positive divided by negative. Or sorry, positive comma negative. Any point in the fourth quadrant is a positive comma negative point. The sine is negative divided by r, so it's negative. The cosine is positive divided by positive, so it's positive. Tangent is sine divided by cosine, so it's a negative divided by positive, so tangent is negative.
Oh, it says everything there.
So the objects that are stated in there, all sine, tangent, and cosine, those are the three, or the one I don't want to say the one, it's the cluster of three that are of the main three that are positive in those quadrants. What I mean by that, when it says all sine, cosine, and tangent are positive in the first quadrant. When it says sine, okay, positive in the second quadrant, and then cosine and tangent are negative in the second quadrant. Does that make sense? Okay. And then the attachment, that if those are the three that are positive in the first quadrant, then their reciprocals carry the same FIGN, right? If sine is the only one that's positive here, then all the other ones are negative. Sine's reciprocal must be positive here, and the other one's reciprocals must be negative here. Does that make sense? So we're going to call this a mnemonic phrase. Like King Henry died by drinking chocolate milk. That's a mnemonic phrase, right? To remember the powers of 10 for the metric system. This is going to say all students take calculus. And what that's for is remembering of the three, sine, cosine, and tangent, which ones are positive, which ones are negative in those quadrants. Then you can talk about the reciprocals when you need to, having the same signs. However, so that's kind of, you'll see that in a lot of textbooks. All students take calculus. If you want to remember other ways, that's fine. But this follows how we kind of name our quadrants in that counterclockwise fashion. So that's how we ASTC as we move around. Does that make sense? Okay. All right, so this is the type of question that we're going to, hopefully at some point, you should be able to tell me that you know this answer to be negative radical 2 over 2, or off the top of your head, like you know 2 times 2 is 4. Okay? But we need to see a handful of these before we can get to that point. Okay? So every time that we do a problem, guys, I think it's a good idea to draw a picture. Okay? Can you do it without a picture? Yes. I think if we go back to geometry, I told you everything we did in our geometry class, we could have done without pictures. Okay? It's just very difficult to keep all that stuff stored visually in your mind, and to be able to look at the notation, all that kind of stuff. Same thing in trig. We can do it all without pictures, but it's very difficult to kind of use your mind's eye to see things. Okay? So put it out in front of you. First thing you're going to do is let's find cosine of 135. We're going to want to know what the exact values are. So we're not going to use our calculators here until we're done to see if what we've done makes sense. Every angle has to be in the coordinate plane. And it has to be in standard position. So we're going to create that ray, which is our initial ray. And now our terminal ray is going to pass through 135. Okay? We always move counterclockwise. So how many degrees would that be? 90. How many more do I need to get to 135? 90 plus what gets me 135? 45. Okay? So 45 is halfway in between that next quadrant, right? Okay. So that angle, call that theta, is equal to 135. Okay. Now, the next thing you do, because what we're trying to do is use a right triangle approach here to evaluate cosine of 135. So right now, we don't have a right triangle. We need to choose a point, and it does not matter what point that exists on this terminating ray. Okay, so you can choose that point, you can choose that one, you can choose that one. It does not matter. Okay? My suggestion, this is just what I always do. It makes things easier, I think, because of size. I always go to the tip of that vector or ray, and I choose that point. And I don't really know what that ordered pair is, and the idea about that triangle in comparison to maybe this triangle is that it shouldn't matter because they're similar. Therefore, their comparison of opposite over hypotenuse or adjacent over hypotenuse or opposite over adjacent should be identical. So it doesn't matter what ordered pair you choose. Okay? Now, I don't specifically know what that ordered pair is numerically, but I do know this. I know this angle right here. I'm just going to call it theta bar for now. I do know this angle right here. What is that angle? Say again? 90 degrees. This one's 90. I'm talking about that one right there. What'd you say, Blaze? 180 minus 135. So we're working kind of backwards that way, right? How big is that? 45. Okay? So we know that angle right there is 45 degrees. Would you agree that that angle, 45 degrees, has and in that triangle, that its hypotenuse is exactly the same as the terminating ray for 135? Okay? So because of that, what you learn about the angle that is at 45 degrees will be exactly the same that you need to know about the angle of 135. The sine of 135 should be the same thing as sine of 45. The cosine of 135 should be the same thing as cosine of 45. Does that make sense? Yeah. Tangent and cotangent, secant and cosecant should be the same for 135 as it is for 45. So here's the thing: 45 degrees. That's a unique type of triangle, isn't it? Yeah. So unique that we call it a 45, 45, 90 special right isosceles triangle, right? What is this distance right here? It's always n, right? Yeah. Okay, now, you can do one of two things. I'm going to do it right now, but you can do this at the end if you want to. I know that if that's 0, 0, and I move this direction, I move left, that n value is really what? If you move left from 0, 0, it's negative n, isn't it? Yeah. Okay. What is this distance here? That's y distance. It's the opposite, but what is the height of? What is that? That distance is n as well, right? Now it's going up, right? So this point right here is negative n comma n, isn't it? Now, in the whole grand scheme of things, I really don't need that point. But if n was 3, it'd be at negative 3 comma 3. If n was 5, it'd be negative 5 comma 5, right? Does that make sense? Okay. Now, here's my question. Cosine is that divided by r. Well, let's look at a 45, 45, 90 triangle. Isn't r n radical 2? Yeah. Okay. So cosine is the x value, or the adjacent side, divided by the r value, or the hypotenuse. If I evaluate those, get negative 1 over radical 2, negative radical 2 over 2, right? Does that make sense? Now, when I'm done, I just got to make sure of this. Is my cosine, all students take calculus, cosine is supposed to be negative in the second quadrant? Yeah. Yeah, sine is the only one that's positive, right? Is my cosine negative? Did our answer just come out to be negative? Yes. So we're good. If I would have worked through this and I got my cosine to be positive, and the reason that people would have gotten it positive is they would have just looked at the 45, 45, 90, and they would have assumed that that was a positive because it's a distance, and they would have gotten radical 2 or 2. But then they got no, well, I'm in the second quadrant, so I got to make it negative. Okay? But here's the thing. Let's go ahead and see what that evaluates to. If I've got square root of 2 over 2 gives me that number right there, right? If I type in cosine 135, does it give me the same number?
Wait.
Yes.
Why don't we just put in our calculator?
Okay, so that's a good question, because eventually I'm going to ask you to square this number, or cube it, or take the square root of it, or something like that. We're going to do some algebra to this number. When you look at that, that's an irrational number, right? So when I square that as a decimal, I've got to cut it off somewhere, right? And then when I square it, that amount of rounding error is compounded, right? That creates a problem in other calculations. Another thing that I want to be able to do quickly is mental math. Do you know what 0.707 times itself is? Even if we did round? You don't, right? So if I take radical 2 over 2 and I square that, don't you know that would be 1/2? Radical 2 squared is 2. 2 squared is 4. 2 over 4, right? Does that make sense? So if you want to leave it as an exact value, it allows us to do algebra later on much quicker and more efficiently and more accurately. Okay? Let's do this. Well, we're going to probably run out of time here. Last class got to this one. Let's see if we can do it. Tangent 390. How many times do I need to go around my circle?
At least one.
One time, and then how much further? 30 more degrees. So one time, and then 30 more, right? So that angle is 30 degrees. Draw down that segment. You're always going to draw at the end of your radius, your terminating ray, you're always going to go down or up to the x-axis. And that's going to create a right triangle, right? In a 30-degree triangle, is this n, 2n, and n radical 3? Okay. So tangent is, this ordered pair would be n radical 3 comma n. Tangent is y over x, or opposite over adjacent, right? Does it make sense? Did I get that? Tangent of 390 is that? Now here's my question. Did I ever really use 390? What angle did I really use? 30. Because 390 minus 360 is 30. So what we find out is that the tangent of 390 must be the same as the tangent of 30, which is the same as radical 3 over 3. But why is 390 the same as 30? Then what kind of angles do we know? Coterminal angles. So what you know about one angle, you know about all of its coterminal partners. Does that make sense? Yep. Okay. So what happens here to be efficient with some of our math, ultimately, if we can learn information about angles between 0 and 90, you can learn about angles from negative infinity to positive infinity. Okay? That little cluster from 0 to 90 tells me everything we need to know about all angles that you could ever make. Okay? Now, there are some, like, let's say 41 degrees, that I'm not going to be able to do this algebra with, right? Yeah. Because I don't know what the opposite and adjacent sides of 41 are, or 41 degrees are. But that's when our calculator kind of kicks in and we can use the information that's in our calculator. Okay. So here's the thing. You're going to use your calculator. There's going to be times, guys, where I'll let you use your calculators, but I will write tests and quizzes so that every single problem on there cannot be done with a calculator.
Oh, yeah?
Okay, yeah. All right. So we need to know these relationships. That's what I'm trying to strive for here. Tomorrow we'll pick up with this again. No new homework. There will be homework tomorrow. I'm not doing 2 questions in 5 days. Why?